My name's David Lynch. I'm a strategy manager at Northern Gas Networks, and I'm going to start by giving you the high-level context for our HyCoRe program before handing over to each of the work package leads to provide some of the headline findings from our project. Next slide, please. So our program was made up of three core partners, Northern Gas Networks, HyCoRe, and Kinnewell Energy. And we also had a range of advisory industry partners, including UKPN from the electricity network. The core focus of our program was to investigate key options and considerations for exporting offshore wind power, with a particular focus on the role of gas and electricity networks in transporting green hydrogen from offshore wind-powered electrolysis. In terms of outcomes, our program was designed to gather new knowledge regarding the future energy system, preferred options around the optimal placement of electrolyzers and energy storage devices in order to inform, hopefully, the next alpha phase of our program. Now, our alpha program, my colleague Paul McKeever will talk a little bit around that a little bit later on, but just some high-level perspective aspirations we'd like to cover in that round will be around establishment of a test facility designed for validating software tools and models, proving out the component technology performance required for future energy system modes of operation as well. We're also going to be conducting in our alpha phase a review of gas network regulations and changes required to accommodate industrial scale hydrogen from offshore wind. So we've got 6 work packages. Next slide, please. What I'd like to do now is just give you an overview of some of the 4 technical work packages. So work package 2, we focused in on investigating the options for exporting offshore wind power. Here we looked at the best offshore electrolyzer configurations. We also looked at the value of storing energy in the pipeline, and we looked at what hydrogen technologies and test and demonstration facilities will the sector need going forward. So a bit of future gazing on that one. Work package 3 was the energy carrier medium. Here we used our partner Kinnewell's clock software to broadly represent and simulate a gas pipeline into a array system, and what improvements could be made to the overall offshore wind farm design, and use that to make a comparison of electrical versus hydrogen systems for export. In work package 4, we also integrated analysis cost drivers. We looked at combining the outputs of work package 2 and work package 3 and looked at the main cost drivers of electrical versus hydrogen offshore wind systems. Finally, in work package 5, the impact on gas and electricity systems. Was there an opportunity there to reduce energy network investments through strategic deployment of electrolyzers, and what are the possible locations? And here we focused regionally in an area in Teesside, but in our alpha program, we'd like to open that up to a national level. We also looked at what are the best ways of using electrolysis and energy storage at scale in order to reduce network infrastructure costs. So I'd now like to just hand over to James Withers from HyCoRe to provide some of the headline findings from work package 2. James, over to you.
Thank you. Next slide, please. So on that first point about optimal electrolyzer configuration, we see that onshore electrolysis is currently easier, but offshore options have advantages around costs, time to deployment, and permitting, depending on the site and capacity. Overall, though, there was a broad consensus that the cost of hydrogen produced from offshore wind could be about £5 to £10 per kilogram today, but that could fall to £1.50 or £3 per kilogram in the coming decades. Next, we looked at changes to wind farm design, and although we didn't see that hydrogen would enable many changes to the wind farm design itself, we did see that it would be promising for allowing sites that are further from shore and in deeper waters to be developed. So we mapped that out as a function of water depth and distance from shore. So kind of near shore, shallow water, electricity is a clear favorite. As we get deeper and further from shore, there's a kind of tipping point. And then for those further from shore and deeper water distances and depths, we think that hydrogen is promising. If we move to the next slide, please. So the third thing we did was a case study with a simple analysis looking at a 100-kilometer long pipeline with a 12-inch diameter. And just based on the pressure difference in the operating range, we found that it could store over 400 megawatt hours of energy through line packing. And on a windy day, this would increase the revenue from a 900 megawatt wind farm by about 1.5%, equivalent to about £11,000 over the 24 hours that we looked at. Next up, we considered the economics of energy transport for pipelines, electrical cables, and hydrogen shipping. They all have their own niche. So ships are best for long distances. Pipelines are most effective in high capacity middle distances, as defined on the slide. And cables are the most competitive in shorter distances. And last slide, please, for work package 2. We had a look at the new engineering challenges that could benefit from new test facilities. So one of those is how to manage a wind turbine electrolyzer microgrid. And we think we can help advance that question by connecting electrolyzers to grid emulators to enable sophisticated electrical testing, or even to a real wind turbine. And another example was that we saw for subsea systems as a question around how can we confirm that current or repurposed pipelines are suitable for hydrogen transmission. So we think there's potential for establishing a submerged hydrogen pipeline test facility. And that's all from work pack 2. Thank you.
Thank you, James. Next up, we have Hamza Sajid, and Hamza is from Kennywell Energy. Hamza.
Thanks, David. I'm delighted to present the outcomes of our study in this work package, which reveals some exciting possibilities for the future of renewable energy. The implementation of hydrogen inter-array systems offer significant advantages. Mainly, these systems require shorter pipe lengths compared to your traditional inter-array cable systems. But more specifically, we found that this can become cost competitive as we scale up offshore projects, highlighting the potential for hydrogen integration. Additionally, our research indicates that pipeline systems enable the substation position to be less sensitive to inter-array costs. Now, this provides more flexibility in the overall project design, and savings in other areas of the system can be achieved, such as reducing the length of the export cable. Moving on to the export system, we also examined the economic viability of hydrogen for a 1.2 gigawatt case study. And our findings demonstrated that projects situated further offshore present more favorable conditions for hydrogen integration. And in this particular case, we found this to be at distances of greater than 150 kilometers. Now, this is a significant milestone as it opens up opportunities for remote and deep sea wind farms to leverage the benefits of hydrogen integration. Next slide, please. So when it comes to the inter-array system, we've identified significant cost differences between pipes and traditional cable systems. Overall, project costs with the use of pipes are considerably higher, and to achieve cost competitiveness, it's crucial to focus on cost reduction measures. So specifically, pipe purchase costs need to decrease to 30% of the current cost assumption. So by exploring alternative procurement strategies and leveraging economies of scale, we can really drive down these associated expenses. Similarly, pipe installation costs need to reduce to 20% of the current cost assumption. Now, in relation to the export system, we evaluated the CapEx associated with hydrogen and electrical options for offshore wind farms. And our study revealed that some hydrogen systems exhibit lower CapEx than these electrical systems for projects located more than 100 kilometers offshore. Now, again, as I previously mentioned, it's demonstrating that potential economic advantages as we, move further offshore, I guess. Now, to achieve a fair CapEx balance between both these systems, cost reductions are required. Specifically, in the case for a decentralized system, we found that the electrolyzer costs need to be reduced by around 25%. Similarly, pipeline purchase costs need to be decreased by about 75%. Now, this means exploring alternative materials and technological advancements to find these cost savings. Lastly, it's worth noting that substation platforms contribute to approximately 7 to 10% of the overall export system CapEx. So optimizing the design and deployment of these platforms can further enhance project economics. Back to you, David.
Excellent, Hamza. Thank you very much. Next up, we have John Nobu from ORE Catapult. John, over to you.
Thanks, David. Next slide, please. So work package 5 was around answering the question around flexibility, and that focused on the impact on gas and electricity networks. So we set out to answer a number of questions. The first question really was around finding a potential location for a future case study in the alpha phase as well. In this, we reviewed the long-term development statements for both the gas and network operators, electricity network operators. And as you can see in the diagrams there, we saw that there is a potential for network congestion relief by using electrolyzers. In this, we saw that from my initial analysis, Teesside was a good region to focus on. That's based on the fact that 90% of the homes are already connected to a gas network. The existence of pipelines and infrastructure plan with Project Union, East Coast Hydrogen, and even in the North Sea with the North Sea cross-border hydrogen pipeline 1 and 2 as well. One thing we highlighted here, we really wanted to understand a little bit more was around the water requirements for a sample in the Teesside region, if we were to go on this with a further case study as well. The second question there really was more about how do you actually introduce these technologies from hydrogen at scale? And we sort of tried to focus on how that relates to costs as well. And that showed us that actually the electricity market structures and also the market and the existing electricity market design is a key factor in that needs to be sort of understood better in terms of understanding how hydrogen could form a reliable sort of participant in existing sort of way markets are run. So the questions there really was understanding that wholesale electricity prices are a main factor, and in order to sort of tackle this would be understanding how the new sort of hydrogen strategies for markets would work. And we're really interested in exploring a further cost benefit analysis in the next phase around understanding if there's an actual potential network we could service, which can identify that could actually be useful to actually prove the viability of hydrogen in the network as well. Next slide, please. The third question really now was we've finished with all the aspects around the networks, but we wanted to focus on offshore wind generation, understanding the potential for hydrogen production from that. So with the same sort of idea that we have identified Teesside as a region, we set out to understand a little bit more how sort of Teesside, the region is in terms of proximity to existing offshore wind farm sites and how they potentially could be used for hydrogen production. So in there as well, we identified that already there are existing wind farms there with capacities above what maybe might be possible to connect to the grid in the future. And there is a potential that some of that capacity could be used for hydrogen production as well. One thing we really wanted to understand was how this would really integrate into the network. And we understood that there's actually existing gas pipelines in the North Sea that can be repurposed and by blending hydrogen in as well. And this is one of the areas we're really interested in exploring further in the next alpha phase case study. The fourth question now was really around these technologies are going to be integrated into the networks, both electricity and gas. Would they actually meet the existing testing and validation requirements to perform if they are to be operated within the network as well? So we looked at two areas. One is grid compliance, which we realized that there isn't so much awareness on how much hydrogen systems, be it electrolyzers and fuel cells, will be connected. And we did see that possibly most of those systems can actually comply, but there's still a bit more understanding into how that would actually happen in terms of the existing policies and regulations regarding that. And the second aspect really was around actually participating in the existing markets. So how actually would you trade hydrogen? And we realized that hydrogen as a technology could actually participate in the existing market services provided by National Grid. But we did see there that there's opportunity there for actually a closer sort of deeper sort of design that will integrate the technologies much better in a similar case of how initially battery energy storage was introduced into the market as well. And I'll hand over back to you, David.
Thanks, Paul. Sorry, thanks, John. And next up, finally from the HyCoRe team, we have Paul McKeever from ORE Catapult.
Okay, thanks, David. So yeah, looking forward beyond discovery phase and what we do next. So opportunities identified. So certainly continued engagement with the advisory board, which has been really valuable so far. And there's also an opportunity to widen that project engagement. And then looking at the work package outcomes themselves. So work package 2, we've already identified the benefits of test infrastructure. 3 and 4 has showed us the value of developing analysis tools. And work package 5, the need for deeper cost benefit analysis for network investments and infrastructure upgrades. And then in terms of the potential benefits of those activities, so that engagement, that stakeholder engagement will help us to improve our knowledge and also avoid duplication from similar projects. The test infrastructure, two reasons really. Firstly, validating our models and also de-risking the key component technologies. And finally, those analysis tools, we can strategically use those to greatly assist our future energy system design and optimization. So next slide, please. In terms of project thinking evolution, one of the big things that we've learned in the discovery phase is the value of a regulatory landscape analysis. So that needs to be in an alpha phase program. So thinking about the alpha phase program elements, we'd certainly want to do more technical, economic, regulatory and market framework analysis. We'd want to develop those tools that we've identified in discovery for managing systems at both regional and system level. Work package 5, further cost benefit analysis, looking how far we can take hydrogen as a service with using initially the Teesside case study. And then finally, more focus on the energy generation aspect, particularly around the wind turbine electrolyzer systems, both from a technical, economic point of view, and also that test infrastructure. So if we can validate those tools, if we can de-risk that technology, then that provides that investor confidence before you really start to go into a big demonstration scale activity. So that's all from me. Thanks.
Thanks very much, Paul. That concludes our presentation from the HyCoRe team. Beth, back to you. Thank you.
Brilliant. Thanks all for a very, very thorough presentation. You have a lot of questions in the Q&A. We're not going to have time to get through all, but I'll try and pick off a few. So how does building the test facility differ from core BAU activities for the catapult? And have you identified any overlap between programs like the Hydrogen Innovation Initiative?
Shall I jump in there, Paul?
Yeah, you can have a go, James. I'm happy to supplement. Yeah.
Yeah, super. So in terms of new aspects around these test facilities, so a big kind of trend that we're seeing is this importance of hydrogen to offshore renewables, and so this is we're pleased to kind of be in the commissioning stages of a small scale system at Blythe that's going to use hydrogen, and that's the first time that we've had hydrogen equipment on site, and so although we're kind of used to working with flammable gases and high pressure gases, the fact that it's hydrogen is still breaking a lot of new ground. So we're covering a lot of safety aspects there, and that's helping us. And once it's up and running, even more so, that's going to help us to tap into electrochemistry in a way that the organization has never done before, and thinking about kind of pressurized gases for energy storage in a way that we haven't done before. And so we're really excited for that. So the Offshore Renewable Energy Catapult is in the Hydrogen Innovation Initiative, and this is we're really pleased that this kind of work is interesting for a number of different funding organizations, and so there is some overlap there. I think in HyCoRe, we're especially thinking about that kind of cost reduction and then kind of strategic placement of electrolyzers as well. Thanks.
Thanks.
Yeah,
oh,
just to supplement that, one of the key things about the HySeed program is it's a seed program, so it doesn't actually do any physical hardware demonstration or test rig development. It's kind of the precursor for that. So there's an opportunity to use the alpha and beta phase programs to really accelerate and get the boosters under that and get maximum benefit from the learnings of HySeed.
Thanks, Paul. Thanks, James. Next question. Has your study found it more commercially attractive for wind farms to produce and export hydrogen rather than power? What key assumptions in your modelling have high and low confidence?
We did a bit in that, but Henna, you go first, if you'd like to.
Thanks, James. I thought I'd just jump in there. So I think what we found is that hydrogen was commercially more attractive in certain situations, and as Hamza said there, it's in particularly far from shore projects that we found it to be most attractive. Your point there about assumptions is an excellent one, and perhaps I can't really go into so much detail on this call today, but what I would say is that the work of Work Package 4, where we were looking at the cost drivers and exploring the impact of those assumptions was where we tried to address that there, and really looking at how much do we need to bring down the cost of the assets that we've got to make them cost competitive with the electrical system. I don't know if you want to add anything there, James or Hamza.
I guess over to you, James, if you want to input anything.
Hamza. Yeah, I think that point about assumptions. So there's so many different dimensions. So just to name like 3 is the distance from shore, the water depth, and the capacity of the wind farm. And there's a whole bunch more besides that. So it's easily like a 7 or a 8-dimensional type of problem, and like mapping that out between different studies. And some of the studies will show loads of information, and some of the studies are more consultancy style, so they won't be as much information upfront. So it's not quite as clear like how to compare them. So I think that's something that we're really looking to drill into in an alpha phase. And I think another thing is there's so many different possible business models as well. So it's very easy to come up with a business model that makes hydrogen look terrible. That's easy to do, but there are options where it is possible to kind of bring it down so that it looks favorable. Yeah, and for example, like taking account of the value of the energy stored in a pipeline, that's lost in a levelized cost calculation, but that would be captured in other economic metrics like net present value and payback period. Thank you.